and also for inviting me. So today, probably I will talk about contact, but also more on the side of how does high resolution sensing play a role when we want to understand contact. So with that said, let me just go ahead and show you maybe some situations where contact happens. And in fact, I think we will all agree in this workshop that contact is at the core of many of our manipulation. And that will also be true, most likely for our robots. But if we look closely at ourselves, I think it's very special and remarkable how we manipulate things. Not only because we can do a lot of different things, but also because of the fact that, and to me this is very important, we can get really good. We can become really skilled at solving one of the tasks that we want to do. So to me, I would like to see robots that as they improve, as they are more confident to make contact, they can also get better at those situations and they can improve over time. So with that said, then just let's go back and look at maybe industry. What are the robots that we have in there? And probably you will imagine something like the video is showing, where in fact, those robots can be really precise. So this is very good. But usually that comes at the cost that now we have one arm or one robot that is only doing one task. And what this means is that usually the set of contacts that it's going to make is also very defined to the task that it needs to solve. And instead, if now we look at our houses, well, you're not going to find many robots. And the ones that we're going to find maybe look a bit like this. So if you wanted to say something positive, I would say those robots can be many houses. But usually that comes also at the cost that they are not very precise. They will, just to say something, bump into things. So even the type of contact that they will do, so it's not always a desired one. But anyway, this is what we have right now. To me, what it's important is that we want to go towards robots that hopefully can be both more general and precise. And for that, I think we need to traverse these two axes. The first one is going to be how do we achieve precision? Second one is how do we also get that with generality, allowing the robots to be able to adapt to new tasks and situations. So with that said, of course, it's going to take a long way to get there. And to me, it started on one of the ends of the spectrum. And as you can see in the video that is playing, here there is a fair contact. The contact is between sliding and sticking, but with this type of contact, we could actually achieve very precise control of an object that is being pushed. In this work, we do get precision, but we get very little generality. This will only work for one object and even just for one surface. So then after doing this type of works, I move into something that is more general, which was the Amazon Robotic Challenge, which I will just briefly describe, but what allows us is to now make more diverse type of contacts and achieve more generality by picking more diverse types of objects. But this is not going to be ideal because of the situations that we are going to encounter. So after this, I would just like to show you how I've been moving towards more sensing. How do we get accurate, precise models for vision, but especially for tactile sensing? And then how can we put those into a more complex system that can do pick and place dexterously? So with that said, I'm just going to start for the first point, which is what happens when you only care about generalization. And this is going to be in the context of the Amazon Robotic Challenge, which for those of you who might not have heard about it, the whole grail of the challenge is you have this bin full of objects. Many of them the robot has never seen. And the question is, how do you pick them? And as you can imagine, a lot of contacts need to happen in this situation. Well, because this is a challenge, you get to do your own system. And in this case, we design our own that has designed a factor that can do two types of contacts. So it can do grasping, suction on an object, or it can also do grasping on it. So these are the tools that the robot has. And as a result, what we get is this system that, as you will see, is going to do a lot of contacts and is going to be able to pick a lot of novel objects. So that is the good thing. But if you're able to look at it carefully, it's not very precise. And as you can see, now it's going to happen with the binder. It's just going to try and fail many, many times. And this is because of the type of perception. It's only vision-based, and it's not even aware of what is making contact and how this contact looks like. So that is a problem. The second one is that it's not able to really handle this contact that it's making with precision. It's just picking, suctioning, very simple motions and actions on the objects. So with that said, we were able still to win the challenge, but there are clear missing opportunities on how we can keep making progress. So today, I just want to mention two of those. One is, how do you get sensing on the contact? How do you get better tactile perception? And second, how do you increase dexterity through this idea of getting more information of your contacts? So with that, now I want to talk about visual tactile perception models. And I want to motivate this with one example. So now I'm going to present you Jess. So she is blind, so she cannot see, but she can definitely sense contact and understand tactile sensing. So as you can see now in the video, she will show you how to take an object, localize it just with tactile sensing, and finally, she will show you how you should use it, as you can see now in the video. And this is all happening through tactile sensing. This is another example that I hope we can see, because it's a bit subtle, how again, only with tactile sensing, she can actually handle and do a regrasp of this object. So now again, because she knows where the object is, she can just go and smoothly make the change of contacts. So with this, what do I mean with tactile localization? This is what she was using, but how do we do that for a robot? So this is going to be our robot, and we're going to be using high resolution tactile sensors. And here you will see the image that appears on our fingers, the fingers of the robot. So once we touch the robot with this object, you can see now to the left that we actually have, to the right, sorry, the tactile image that shows us an imprint on how the object looks like. In this case, the question that we want to answer is, what is the pose of its object with respect to the sensor? In this situation, this is again the object. It becomes clear that the contact is made in this exact location. So if we were to answer this question, we will be able to say, this is the pose where we are making contact, just based on the tactile image. However, if we now look at the different object, what happens now is that you are going to get another tactile image. Same question, what is the object? But now it turns out that there is two options that can actually explain this tactile image. So we're going into the regime of uncertainty of what we call non-unique contacts. And this is very important for tactile sensing. There is contacts that could actually be explained by more than one pose of the object, and those we call non-unique. Now, how can we deal with those? We still want to be able to give an answer to the question. Well, what we can do then is just think about pose distributions. Instead of a single estimate of the pose, we're just going to say, these are the possible poses that explain this tactile image. And this is what I'm going to be showing you today. And the assumption that we're going to make, and this is important, is that we have access to the object model. But as a result, we're going to be able to solve this problem with providing pose distributions rather than single estimates, and no need for real data. Only in simulation, we are going to learn how to localize any given object. So in a nutshell, how does this work? In simulation, you have the object model that you can actually take and compute contact poses in simulation that now you can transform into simulated contact images, which are these black and white images that show us where contact is happening. On the real side, what we do is we take our tactile image and use a very simple neural network to transform it into contact. The good thing about this is that this doesn't require any knowledge about the object. All it needs to do, this neural network, is to say which parts of the tactile image are in contact, which ones are not. Now, if we combine with the other side is object dependent, but it only happens in simulation. So this is no problem, you can just do it offline. And the important thing here is that we have reduced the problem of tactile localization to a problem of matching. The question that we're going to answer now is, which of the simulated contacts is actually more similar to the one that comes from the real sensor? And if we're able to do this matching, which we do, and you can see the details in our paper using an embedded similarity function, using embeddings for the contact images, now we can just give a pose distribution, which is exactly what we wanted. We're going from a tactile image to a possible set of poses that explain that tactile image. And I have been explaining this for tactile, but it turns out that you can do exactly the same thing for vision. In this case, we're getting a depth image, and your goal again is to localize this object that now appears in yellow. And we can do the same thing. In the real sensing images, we're just going to take crops. But then in simulation, we can again use the object model to also simulate and render depth images. That now, as you can imagine, all is left is do this comparison. And finally, this again gives us a pose distribution for our initial depth image about where is the object. So this is our approach for localization, using both vision and tactile sensing. The question is, how do we use it? How do we benefit from this information to actually allow our robot to become more dexterous and do more embedded interactions with the world? So this is where I'm going to go now on how do we actually solve the task of pick and placing. So pick and placing, you can imagine we have this robot and it's going to go in the following way. We're going to have some objects that we don't know their poses. We're going to pick one of them, and then we want to know where it is within the robot's hands. So answer the question of what is the pose of the robot, the object, with respect to the robot. For that, we're going to use the tools that I already explained, visual and tactile sensing. And once we know that information, then our end goal is going to be to place the object in one of these locations. But for that, we might sometimes realize that we need to do a regress. The initial pose of the object is not good enough for us to go and place. So there's going to be sometimes a regress that is needed. This is an important problem because you're going from a setting that is unstructured, you don't know where are the objects, to a setting that is now completely structured because you know exactly now where you have put the object. So if you were to be in industry, this would just go ahead, go into a machine because now you know exactly where are the objects. So imagine you have them in a box, leave the box there, a robot takes, puts them in a structured situation, then everything else is set. Problem, because we want generality, we want to be able to do this for new objects. This is something that industry doesn't yet know how to solve properly. And in fact, if you look at industry, most of the times it's a human that actually does this work. So here you see how it's doing pick and placing and even doing a regress in order to be able to place this object. So how do we tackle this problem? Well, first, I want to just show you how it does, how the robot does it. So here you can see how it's picking the object. Once it's picked, it's going to use both tactile because it's making contact and vision to estimate this pose. And finally, once it knows the pose, it can compute what is the right set of motions, the right set of contacts that it needs to do, so that it's able to, in the end, very precisely place the object into the right location. And again, for us, the important thing is that we want to get generality. And that requires to know the object shape, but as a result, we can do it without any real experience. Only by leveraging simulation, we are going to do this kind of sim to real transfer so that we can still get very precise manipulations. And this is going to come because we are going to have accurate perception, but also going to rely heavily on task-aware planning. And this is when I'm just going to give you some extra sense of how this task-aware planning works for us, because it really reasons about how contact is going to look like. So the first thing when you're making and grabbing an object is that you want to get a good grasp. But if you look at the situation, this is not a good grasp. So the first thing that we need to plan for is what is a good grasp on an object that is going to just allow me to lift it. So grasp stability, if you want. The second thing is also, and this is more subtle, I would say, is about perception, observability. So if you now make contact, let's zoom first in, and we now make contact in this object, when the robot closes the fingers, it's going to get some tactile imprints. And in this case, these tactile imprints are what we already called before non-unique. There could be more than one pose of this object that can actually explain the contact that we are making. This is a problem. This is not ideal because, for instance, in this case, it leads to a perception failure. The robot thinks that the pose is this one for the object and it's actually this other one. So what this means to us in practice is that this is not a good contact. We want contacts that really give us what is the object. They give us observability, but this is not. So this is another thing that we want to take into account. And finally, there is the end question that you want to simplify the motion, right? Some contacts we know are going to be easier for us to just do the task that we want to do. Others are going to be harder, like taking a hammer. You know that there is a place where you really want to grab it. So similarly, for this situation, if you think about this type of contact, what happens is that it's going to take you 2 regress to actually place the object. So let me just show you. It takes 1 and 2 regress to be able to place the object. While this other contact, what happens is that now you only need 1. So just with 1 regress, you're able to go ahead and place the object. So if I were to ask you which one is likely to succeed, which one requires less motion effort, clearly we would prefer to have this one. So in summary, we really need to be aware of where we're making contact, not just to get a stable grasp, but actually to simplify perception and further planning. So if you put everything together, the system looks something like this. We're getting some sensors inputs These are going to be depth images and tactile images. We have already talked about those. And now the idea is that from the depth image, we're going to do two things. First, we're just going to sample possible grasp, and we're also going to get a vision estimate of the pose. But from this, the first thing that we can now do is do grasp selection. So as I've been talking about before, we can basically try to aim for grasps that are going to make us happy. Happy in the sense that those are going to be stable grasps. They're going to be observables. Perception is going to have an easy time to localize the object. And finally, they're going to simplify how we place the object. So once we had selected the best grasp, we can just exert it. And once you make the grasp, now you're making contact. And this is very important because now you have a chance to further improve your estimate from vision using tactile sensing. This is exactly what we do. We get a bit of our estimation that now takes a very close look at where the object is making contact. And because of that, it refines our estimate. And because of this, then we can just go ahead and plan what is the right set of motions and execute it. The important part of this thing is that we actually don't require any real data. All these parts here are just learning simulation, but they are able to transfer well into the real system, as I will show you just now with some videos. But this is the important part. There is no need for real experience. Simulated data, as long as you have a sense of the object shape, you're good to go. So this is just one example that, again, we will do a regress, and finally we will place the object very precisely. We are going to publish results very soon on more than 10 objects with different types of shapes and sizes. This is just a case where you don't need a regress, for instance, so you can just go immediately place the object. And this is just another one that is a bit more complex shape. But again, just by doing this regress, you can just enable that the robot can place the object with precision. So with that said, I just want to add an extra idea on how I think we can keep making progress on improving how we make a contact and become more general and precise. And this is, to me, forces. I think there is a lot that we can do if we reason about forces. And to me, I want to make a comparison. When we estimate contact, this is something that just give me an image, I tell you where contact is happening. Forces instead are much more than this. They are vector fields. They actually just not like a single patch, they're more than that. And also, they are temporal sequences. So now, if you look to the right, I want to look at this picture because as we move the object, you're going to clearly see how this is a vector field, how the forces that we see in this image are vector fields, but also how they clearly evolve over time. The question to me is, how do we make sense of this? These forces are everywhere when we're making contact, but we don't yet have the right intuitions to give sense of them so that we can really use them. I think there is a lot of effort that I would like to be doing, and hopefully more people will join so that we can keep making progress on how we make contact and how we understand how these contact formations are happening and how we can exploit them later on. So with that said, again, my goal is to move toward both generality, but without compromising on precision. I think this is really important to really get into very dexterous robots that we can ideally have at home. Of course, it's going to take many paths, but I think that's important, right? The fact that there is many different ways that we can follow so that we can get into that direction. And finally, I just want to take a moment to thank all the people that has been involved in all these works, because it's been definitely an effort that takes a lot of minds and people to do it. And with that, now if you have any questions, I will be very happy to take them.
All right, hello. All right. Questions for Maria from the room. We can also potentially get questions over Zoom.
Hi, this is Ken. Can I ask you a quick question, Maria?
Yeah, of course. Go for it.
Maria, what a great talk. I have to say, such an interesting way of putting things, and I really like. One thing I wanted to pull out is the idea of observable contact.
Mm-hmm.
So, in terms of tactile observability, it's very interesting. Is there a way of, and this is related to the training set that
Yes.
you observe, is there a way to systematically explore an object or and I think it also relates to maybe design for assembly. In other words, maybe, okay, I'm just wondering if you could say a few words about that.
We have found that we can, to some extent, systematically find what are contacts that are observable and what are the ones that are less likely to be. So we could definitely try to engineer some instruments, some new tool that I want to use, maybe in an assembly line, so that we can definitely put on it some of those features that we know are going to make it very observable, but at the same time, they are going to be located in a place that we know is also going to be useful for the downstream task. So given our experiments on this kind of pick and place situation, we can definitely find clear regions that are observable. Therefore, we are going to have a very good time localizing the object. I think that could be exploited further down. And I think design would be a fantastic place where you can benefit from that. So I think that's a very nice question. Yeah.
Thank you.
Hey, Maria, nice talk. One question I had, everything that you showed was pretty much focused on high precision, very careful manipulation. How well do these tools, both hardware and software, generalize to dynamic manipulation tasks, do you think?
Yeah, that's a very nice question. I think right now, yes, some of the tests that we are doing, I would say, are more on the slow end of what we would like to be. But we are also working right now on tracking. What if you just get the first estimate of the object, but now you can very quickly update it so that now you can allow more fast. And we would like initially to even look at in-hand manipulation, right? You just move the object around, but you have these tactile features that you can keep localizing and just get a very good estimate so that you can close the loop very fast. And I think we can do it because our tactile localization as it is right now already runs at around 30 Hertz. And I think combined with other tasks that just make the search, let's say the selection more sparse, we can definitely see this working for even faster regimes. We are working towards some of that, but I do have hopes that this matching that we are doing to select what is the set of poses that can better explain a real observation can actually be fast enough so that you can solve this in more dynamic regimes.
Okay, great. And then we have one more question over chat.
Yeah.
Can you roll the object with the tactile pads automatically? Like what you did with the chess piece, but with no human interference, or passing them from one arm to another and combining them?
So definitely passing from one arm to the other, yes, we can do that. And I think that would be already a way to do, I mean, we're already doing this passing. In terms of the rolling, that's a good question. And the solution that we are finding in my lab is that we might want to adapt a bit the type of tactile sensors that you're using for that. So I will be honest, with the current sensors that we have right now in place, because the type of friction that we want usually is a bit more sticky, it would be a bit hard. But actually our second version wants to do in-hand manipulation. So we're going to reduce a bit the friction, which is going to also reduce a bit the quality of the tactile sensing. But as a benefit, we're going to be able to do more motions that are in hand. And I expect that rolling against the surface will also be one of them that we can explore. So I would say there is a design there on how you make the hardware, but as long as you're willing to do it, I think some of those tools will be able to actually transfer to these systems. And even rolling could be something within the scope.
Okay, great. Let's thank Maria again.